Hi and welcome everybody to my 2 days presentation about the software project SDEval, which promises and holds the promise of providing some benchmarking possibilities in the field of computer algebra. My name is Albert Heinle, and before I start I would like to acknowledge the Deutsche Forschungsgesellschaft, DFG, for financial support of the development of SDEval in the context of a priority project called Algorithmic and Experimental Methods in Algebra, Geometry and Number Theory. Okay, let's provide quickly an overview of the talk. I don't want to talk too much about the background of SDEval, how we came to it, and our philosophies. I more like want to present a hands-on in a hands-on way how to use this software. So I will keep the first part of my presentation, the introduction, very short. Then I will go directly into the demonstration of SDEval. Then, of course, I will provide you with some possibilities, hint hint, for contribution to SDEval, and we'll conclude with some words about future work and what we are still planning to do within this project. Okay. Let's start with this. So where does it come from, the idea of SDEval? So in 2011, Grisha Studzinski and Viktor Lewandowski, they came up with a new paradigm to compute Gröbner bases in free algebras up to a certain degree, and it had the code word singular letter place. So, and they wanted to benchmark their implementation, whose like really, it's essentially different, the approach is essentially different from existing ones, against current implementations. So, and there were two problems which were occurring. For every computer algebra system which you could use, I will sometimes abbreviate it with CAS, the way how to enter examples to perform a desired calculation differs by a lot always. And sometimes the calculations are very resource hungry, especially when it comes to Gröbner bases. So what can happen is, like, for example, you want to calculate a certain example overnight. You just start it on a shared computing space, and in the morning you get a call from the admin asking you why you used up 90 gigabytes of memory and is very mad at you, but of course you didn't check it overnight, so it did actually happen. Yeah. And an observation that we made is, these problems are not just concerning this special project, but these are to be found all over in the field of computer algebra and in the computer algebra community especially. Okay, so and then we formulated main goals for SDEval. So first of all, if you write a paper and you have, let's say, a piece of software that you provide with your publication, then often we see those tables where there are timings and they say we were this fast, another software was this fast, and things like that. Very rarely, from my experience at least, people are actually providing the files that they used for computations, the ways how they actually calculated those examples in the different systems. So one of our goals is an easy reconstruction, as easy, and with easy we mean as easy as possible for a person who just wants to run those on his own machine or on a machine that he has access to. So then there is the problem which I mentioned before, that you don't want to learn all those computer algebra systems that are available out there, right? I mean, they have even different philosophies behind them, and you don't want to waste your time, even sometimes, to just learn it in detail to know how to perform certain computation in the best way there. So what we wanted to have is like some way of translating examples where you just take the main content, the input of the algorithms, and translate it into executable code for those different computer algebra systems. Once this is done in a separate sub-project, you need like some sort of way to run, observe, and automatically stop calculation if some user-provided limits are given, i.e., as I meant, not to make any admins angry after you have used up a lot of resources on their machines. So this is basically dividing the whole problem into two sub-problems, which are pretty much distinct from each other. So there's this, what we call the create task. We refer to this collection of examples and computer algebra system as a task. So you create, you translate, and you specify which computer algebra systems you want, and several other parameters that you want to be set. And there is the running task, or the run task part, which deals with actually running the benchmark and comparing the different computer algebra systems on certain particular examples for your computation problem that you are dealing with. Okay, so, but of course, in order to translate examples, we need examples, right? So we looked around and wanted to decide for a certain database that we use to translate from into executable code. And we decided for the Symbolic Data project, which is a more than 10-year-old project, and it is a collection for problems for the computer algebra community. The entries are constantly updated and are given in XML format, and they pretty much keep it up to date since 10 years. And XML is especially good for parsing it into any programming language you want. So that means we were not tied to a specific programming language in our project. So, and what they also do is they develop ways of accessing even entries in other databases by interlinking, and I don't want to go into details about this, but there is in this paper, I think here, a description how they use the semantic web techniques to do this. Okay, so Symbolic Data was basically the database that we decided for this project. Okay, and now we come to the main part. So, and now here's my little cheat sheet, what I want to present you. So this is not of too much interest for you, this is just for me to see if I have shown everything I wanted. So, first of all, what I'm going to show you is how to access the database and translate certain problems into executable code in the computer algebra system. So, I'm here in my terminal, and I want to do it the GUI way. We have a GUI and we have a terminal way. So the terminal way was, we thank Benjamin Schnitzler for doing this, is if you are, let's say if you have SDEval on a remote machine and you can only access it via SSH. So, but here I can actually do the GUI way. So I just try Python and create task GUI py. And if I press enter, hopefully a window will appear. Yes, it does. So, and here I can choose from certain computations problems. So, for now, there are computation problems which we were particularly interested in for translation. So this project is extendable. That means we just have to add one more file and there will be a new problem appearing there if we can deal with it. But let's say we want to do a classic Gröbner basis computation over the commutative ring. So if I click next, I see here a list of several classical examples all listed from this database. We can look at it. So there is a classic one is the Katsura 3. So here you see what variables there are, and this is the basis, it's a set of generators. So if we want to add this, we just click add. We want to consider it for a computation, or Katsura 7 even, which is a highly complicated problem. So if we, and let's say we content ourselves with those two examples, okay? In the next step, you would choose the computer algebra systems that you want to use. So we are, by now, we have written templates for translation for these computer algebra systems. So I know, for example, I have Singular on my machine here right now, I have gap. So then what you do here in these fields is basically, you know that commands to call computer algebra systems are different on every machine. So that means here you actually type in the command for your specific machine how this software is called. So for me, this is definitely Singular, how it is, and I only need gap. So in gap is, I think, smaller case letters. Time, so the time command on Linux machines you will probably always write time. We gave you a certain freedom if you want to choose a different timer to do that, but the only thing that it needs to provide is an output which follows the POSIX 2 standard. So, and here I give this thing a name. I call this the SCG lab presentation. I hope I didn't do a typo. So, and then I click here, and then I choose where I want it. I actually want this on my desktop. Okay, so and then it says the task was successfully created and it closes itself. So what did happen? So if I go to my desktop now, I see here a new folder appearing. Okay, so in this folder is what we call a task folder. Okay, so this structure is now completely distinct from our creation part. So here you have some freedoms how you want to execute things. So there are only some things that need to appear here. There is this 2 XML files, which are machine settings and task info, and these are executable files from the SDEval project. You don't have to worry about this that much. And up here you find the sources for the computer algebra systems. If you go, for example, to Katsura 7 and want to see how singular works, then you click on this file here and then you see how you would tell singular to calculate this. And what I mentioned earlier, that is really different from computer algebra system to computer algebra system. I mean, if you compare this to GAP, this is a total different command list, and you don't want to really learn this. So that's the point. Okay, so far, so we have, let's say, this is generally the structure of the of our what we call a task folder. So what we can do here now is executing this script called run tasks pi, and here, if I go to my terminal, SCG, yeah, okay. And if I now type in here Python run task pi, so, and I want actually first to do minus help, okay, so to see what I can do. So there's certain things that you can call this run task with. So you can specify a maximal CPU time that you want to use for your project, and then it will cancel the task automatically if it didn't finish by then, right? This comes in handy if you want to have a bunch of examples and see which ones are, let's say, faster than 2 hours and you don't want to control it by hand. So then you can here make admins happy by specifying a maximal memory usage, and as we all have usually more cores than one, you can also do several jobs in parallel, and this goes with the flag -j. But I want to just do like everything without any special flags set. So if I put run task pi, so nothing happens. If you go to the folder, here a new folder appeared called results. This folder has a subfolder which contains basically information about the current calculation that is running. So we have a certain visualization of what's going on. So if you click on this here, HTML, and then you see, okay, this here already ended, and the color green indicates it could extract a certain output from it. So and it seems to be all right here, and this here is still running. So you basically can go in the morning to your office and look, oh, my calculations are still running. So now assume you figured out let's say you didn't set an automatic termination flag, but you want this to be done because it kind of stops your whole process, and you don't want you see it's not going anywhere. You can actually just stop this one process manually without interrupting this whole system, right? So you can manually stop this and nothing happens, so you don't have to restart everything all over again. So if I go, for example, top here, and I see singular is running here, is all right on top, then I killed this process, 8107. Okay, now it is replaced by gap. If I refresh here, you see something went wrong here. So this means this is the color code. There is like, it's terminated, but yeah, you have to look into the files to actually see what happened. And here, well, gap will probably also not terminate, so I kill this now too to be done. 8253. Okay. So. Okay, and then after that, you are done. You have two killed, let's say, processes, and two which have finished completely, and you have some information stored. For example, now what can you do with this? So let's say you have done this calculation for your paper, okay? and you publish it. So a person can now see here from these files which CPU you have used, has some information about your memory, some information about your operating systems, and can actually look into the files and see what actually the results were. Let's say I go to Singular. Okay, I went to Katsura 7, which is not terminated, but if I go to Singular here, you get in XML format the solution presented and can even automatically keep parsing it. Okay, so the thing is, till now it seems like we can only use this thing for the computation problems that we have by now defined, i.e. Gröbner basis. But that's not true. You can put anything, let's say, in here, any files. The only thing that you have to maintain is this folder structure, right? So if you have like a folder called cast sources, and in here define all the problems, and as subfolders the respective computer algebra systems, you can run almost any calculation there and make use of this running utility. And the good thing about it is, and I cannot stretch this further, is it is easily reproducible. So that means, let's say you download my files, right, and you want to reproduce the results. So back in those days you need to call all computer algebra systems on the files that I maybe provide. Here, you just have to go, if you are on your machine, to your machine settings XML, change some parameters, let's say the calling commands, and that's it. And then you run it on your machine. So this makes it actually easily reproducible for you. And yeah, I won't go into too much detail about this task info. The task info actually assists you if you, for example, we now have seen Katsura 7 is pretty, doesn't terminate pretty quickly, so we want to kind of keep it away from our future calculations. Then we would just comment it out here, and this would not be considered for the next calculation. So this is like the ways how to manage this if you want to, let's say, have some flexibility in there. Okay. So let me look at my cheat sheet, what I also wanted to show here. So we have the organization of the task folder. Okay, I want to jump quickly into the last point, take this a little bit in advance. Of course, one has to practice what one preaches, right? And for former papers that I have written in for example, the one for ISAC 2014s. Here you can find the timings and the task folders on my website, and you can download it. And if you want, you can also do the calculation. So the thing with the output analyzing, if the output makes sense, is fairly new. So that means in the newer ones, if you click on timings, you have this red thing here, right? You have all the things that didn't terminate as expected and the green ones that did terminate. If you click on older ones, let's say for this here everything is green because we didn't have any output analyzing technology yet implemented. So, but what gives it away is that the time limit was reached, and we have mentioned this in the paper. But this is like, you might get confused with older versions that we had from this. But this is just a little warning here. So yeah, and in this way, if anybody has like doubts or whatever about the calculations given in some papers, they can just reconstruct it here. Okay, so now we are talking also about so how does it really look like if you use it for other projects. So I mentioned the ISAC paper. As you know, I maintain a factorization library in Singular for factoring polynomials in, for example, while algebras. And here I created also a folder like that. And as you can see in my result files, I kind of keep track of the results and the performance of the software over time. And as you see here, you have the complete freedom to use it for any software project that you have, and I highly encourage to do so, because this will lead to at least some standards of reproducibility in computer algebra, which is given in other communities that that do computation, for example. Solvability modular theorems community has certain benchmarks and standard sets, and we in computer algebra, we don't have that yet, and in the future I would personally like to see that to do some fair comparisons. Okay, so now we will talk a little bit about how one can possibly contribute to the SDEval project. So let's say you are familiar with a certain computer algebra system and you know how to write, let's say, a little template to do a certain computation on it. So if yes, we have made it actually pretty easy for external contributors to do that. If you go, for example, to this classes file here, here is a subfolder called templates. Okay? So, and if you go into comp, which means like some computation problems, those are abbreviation. You can find them in the documentation to the different problems that we're already dealing with. And let's say you know how to you know how to do compute Gröbner basis in this other computer algebra system. So you just create another subfolder here with the name, and in this subfolder, I will demonstrate it for Riza Azir, there is this template pie. And if you want, you can also optionally put the template solution pie, which analyzes the output and extracts the important information from it. So, but in this template, how you can see, it's basically always looking in this the same way. You have a function called generate code and the essential inputs. So for one computation problems, you have always the same inputs. And then you need to provide us just with a formatted string how to enter it in the computer algebra system, and this is how you extend it. And I could just write, copy and paste this into a different folder, and there is a new computer algebra system added. So it's fairly easy. We try to keep it as easy as possible to extend from people from outside. So then, do you know any other interesting computation that can be done using the existing tables that are already in the symbolic data project? If yes, and you know Python, splendid. Just write a specification in what they call the comp table in symbolic data and implement the required scripts to SDEval. If yes, but you don't know Python, go to the last line, namely send us a wish list, what you want to be considered in the future. And of course there are more ways to contribute. Details can be found in the document Q&A and the documentation. Okay, so now what we have seen here today is software for benchmarking and translating symbolic data entries into executable code. We also have seen what we also want to have right now is to process some user feedback. Right now we have used it mainly for our own projects, but yeah, of course we are highly interested in feedback from other users and see what their problems are. And so that means ask as many questions as you want, and send us emails. In the present and the future, we right now can extract output from the computer algebra systems, but we cannot really yet check the correctness. So for this, you mostly have to also run a computer algebra system to compare, let's say, two outputs of two systems to check if they are really equal. We have to agree on standards. Right now we have found a way to just like extract it, but the interpretation is definitely a work for the future. Then some more scripts for visualization. As I mentioned, I used it for the library ncfactor.lib for singular, and over time I want to see how did it perform over time on certain examples, and some scripts for visualization would be highly useful, but more a bonbon than a necessity. And in the future we also plan, of course, add more and more and more and more computer algebra systems and computation problems to the repertoire. So yeah, and that is it. And normal question is, of course, where do I get this? The latest version of SDEval can be downloaded from my GitHub account, which you can also find on my website, and I will put it on the comment section below. There is a general symbolic data repository there, but they get only pull requests over time. So the latest version can be only found usually on my GitHub account. So in general overview of SDEval and symbolic data is given in this publication, which I will reference in the end. And if you want to know more about symbolic data, this is the link how to obtain this information. Okay, I thank you for your attention, and I'm open now for questions.